Okay, so here we go with our lecture, first lecture of this week. Since we're having the second midterm on next Monday, I just remind you that I posted the timing and so on, in Blackboard. It'll be regular class time. You'll get it a few minutes before the start of the class time, and you'll have a little bit of time following the end of class time to upload it into Blackboard. Please take a little time to think about how you're going to do that, so that we don't have to go through issues so you don't have to go through issues at the end of, oh, this didn't work, or I didn't think of this or that. Another thing, and this is from my prior experience with this stuff, please make sure that as best as you can, the scanning or whatever you do to create the digital, the copy of the stuff is clear. So don't write tiny, and use paper, and try to do the best you can with the quality. Okay. The material, as I'm certainly interested in knowing, for the second midterm covers up to today's class. In fact, we will not really do anything that is really new today, other than illustrate the application of things that we've already have discussed. But in any case, the material up to today, it's what's in the midterm. And the material begins at the end of the first midterm. So nothing that was included in midterm 1 is part of midterm 2. Okay? With regards to, let me think, the part that we did, on stress and strain, was a little bit less emphasized, let's say, with regards to what we've done with the computation of deformations using virtual work. So the exam will be fundamentally on the computation of deformations using virtual work, which is what we're doing now, and we also have the double integration method that we did for the calculation of deformations on beams only. Out of those two things, which is what comes to my mind right now, the emphasis is certainly going to be on the material that I'm talking, of the deformation using the virtual work theorem, which is what we are going to spend the rest of the time doing today. So what I will do is take one of the homework problems that you had, and I'm going to problem number 3, I think, in the last set that Ishmael posted, which has a hinge in the middle, which I suspect might give problems some, and hopefully use that example, that problem, to get you to reinforce your understanding of this subject. I will not substitute numbers in it, but I will get it done 99%. So your task will be, when you submit the homework, to make sure that when you do it, you understand every little step, every little thing that is done through it. If you do that, you should be well prepared. Okay, so let's begin. The problem was, or is, pertains to a frame that has a hinge in the middle, is doubly pinned at the 2 supports, and has a concentrated load P in the middle. Now, one of the questions, the problem in the book, or in the one that we posted, has actual dimensions, but I am going to use symbols that actually respect those dimensions, in the sense that this distance here was 80% of the height, and so I just take it as 0.8 h. It makes it so much easier to follow and to study if you have symbolic solutions instead of just numbers. Now, a first question, and the question was, this is A, this is B, point C, point D, and point E. And the question is to calculate what is the rotation at point C on the left side of the hinge. So this negative that I put on top of the theta C means left side. That's because at a hinge there is no continuity of slope. So there is a slope at this point on the left side of the hinge, and there is a slope at that point on the right side of the hinge. To illustrate more clearly, consider that you had, for example, a beam like this with a hinge and some loading. Doesn't really matter what the loading is. The point is that because of that hinge, there is no moment at this point, but there is also no continuity of slope. So this structure will deform, let's say, or could deform like this, and then like this. Okay? So you can see that this here would be, if that point was B, right, that angle would be the angle at B on the left side. While this slope here, right, would be the angle at B on the right side, right? So at the location of hinges, moments are zero. Here, you cannot transmit moment from one side to the other of the hinge. And because you can't transmit moments, slopes are discontinuous, okay? I mean, by chance, by coincidence, in some cases, you may have a continuous slope, but that's just by chance, right? Okay. So, here we are asked to calculate the slope on the right side of the hinge, on the left side of the hinge. The next question that students usually ask, because they get confused, is where is this load P that it's in the middle? Is it on top of the hinge? Is it on the right side of the hinge? Is it on the left side of the hinge? Okay? Now, that question, the answer is the load is either on the right side of the hinge or on the left side of the hinge, because the hinge has zero dimension, and therefore the load is not on the hinge. Of course, it has zero dimension in the mathematical idealization, right? In reality, the hinge would actually be something physical, right? For example, this beam could be a thing like this, and then at point B there could be a tapering, and then, you know, a circle here like that, and then there could be a thing like this, and a thing like that, and that could be C, and then there's a bolt that goes through it, or whatever you'd like, right? So that is really a hinge, in the sense that these two bars can rotate relative to each other at the hinge. For mathematical purposes, of course, we are idealizing that as a point, like this, right? The load P, for computational purposes, it really makes zero difference whether you consider it to be on the right side or the left side of the hinge. So you can take your choice, but you don't need to worry about which side it is. And of course, to me it's obvious, but I hope that to you it would also make some sense, that if you were to move that load 1/1000th of a millimeter in one direction or another, so that you're on one side or the other side of the hinge, that you don't expect that this structure can actually know that you've done anything, since the load is basically on the same place. Okay? The issue of whether the load is on the right side or the left side of the hinge becomes important, or can be a confusion issue, when you make free body diagrams, because you can wonder, is my load here or is it not, and so on. Okay, so the next thing is, so this is our problem. We have a frame like this. We want to calculate the rotation on the left side of the hinge. So what do we do when we have to calculate rotation? When we have to calculate rotation, we apply a 1 kip-foot moment at the location that we want the rotation, right? That becomes our unit load diagram. So that means that in this case, we want to take our frame, here is the hinge, and we want to apply a unit moment acting at the hinge. Now, this moment, it's on the left side, right? It's not at the hinge, because the question was, what is the rotation on the left side of the hinge? So I have a unit moment. I won't call it 1 kip-foot, it's just a unit moment in the units that we are working on. Could be pound inches, kip-feet, or Newton meters, or whatever, right? Now, sometimes people get confused also as to how is it that I'm applying a moment at that point. It doesn't seem obvious, and I can see that. So I'm going to draw something here that hopefully will clarify that issue for you, and then I'm going to erase it before we start calculating. Imagine that before the hinge, I put a crossbar like that, right? And then the hinge is right here. And then here is the structure, right? Now, if I want to apply a moment, I can do this to the crossbar, right? That being a crossbar. Now, if I take that distance between these two loads to be A, and I apply loads here which are 1 over A and 1 over A, that is applying a 1 kip-foot moment at that location, and that's it, right? So this will produce, this physical arrangement here is exactly this drawing over there, okay? Of course, that crossbar is rigidly connected to the structure here, right? Just before the hinge. Okay, so that's how it goes as far as the physics and the understanding of the problem. So we now need to just do statics for a while. In fact, there isn't really anything else here, but just do a bunch of statics, right? And keep track of our assumptions regarding directions and so on. So this is our 1 kip diagram, or our unit diagram. And then we're going to have to do our P diagram, which is this one, right? Because I'm going to require a number of free body diagrams and so on, I'll probably have to erase if I want to be really precise in describing every single step. So I need to calculate, the problem specifies that we should do this calculation including both the effect of bending and the effect of axial deformations. So I look at it and I say, can I get away without calculating the reactions? It doesn't look like I can get away without calculating the reactions. So my first step is going to be to compute the reactions on this frame. Now, I can probably calculate these reactions, well, not probably, I can certainly calculate them without doing any free bodies, just because I can see the statics in my head as soon as I look at it. But I'm going to follow the systematic approach. So I'm going to take this reaction and call it R at A horizontal, vertical. Put the little thing I'm using to erase here. this is going to be my RA vertical. This is my R at A horizontal. This is going to be, although I know it's not in that direction, my R at E vertical and my R at E horizontal. Okay, so let's say that our task right now is just to calculate those reactions. We'll worry about things on the moments and axial forces later. So first, I could take a free body diagram of the complete structure. I know beforehand that from a free body diagram of the complete structure, I'm not going to be able to calculate all these reactions. Why? Because there are 4 of them, right? And I only have 3 equations of equilibrium in a 2-dimensional problem. But that doesn't mean I can't get some of them. So from a free body diagram of the complete structure, which in this case is the whole thing that we see here, I can say, for example, that sum of the moments about E is equal to 0, taking clockwise as positive, and I see that RA vertical multiplied times 1.6 H, right, that's clockwise, plus what? Plus 1, because there's nothing else, right? Because this RAH horizontal goes right through it, and those 2 are there, must be 0. From where we conclude that RA vertical is equal to minus 1 over 1.6 H. Now, we can then do sum of the forces in the y direction equal to 0, taking upwards as positive, and we will have that RA plus RAV plus REV must be 0, right? RAV plus REV must be equal to 0. Therefore, REV must be equal to minus RAV, and therefore REV is equal to 1 over 1.6 H. Okay, that's about it, because some of the forces in the x direction will not help me, right? All it will say is that RAH minus REH is equal to 0. Oh, I shouldn't say it doesn't help me. It tells me that the 2 horizontals are equal and opposite, but it doesn't tell me what their values are. So, in order to be able to erase and keep things, instead of writing RAV here in that direction, I just simply put what its value is that we just found. So there is a reaction here equal to 1 over 1.6 H going down. On this other side, we have a reaction of 1 over 1.6 H going up, and we can then erase this thing here. Right, so that's our situation. Now, we say, okay, so we're done with that free body diagram. We cannot do anything with that free body diagram, so we must do something with a different free body diagram. So in this case, it's clear that what I need is a free body diagram that takes into consideration, or that takes into account, or that takes advantage of the fact that I know that at point C there is no moment. Now, I could take a free body diagram that cuts through Z and closes a bubble on this side, or I could take a free body diagram that cuts through the hinge and closes on the other side. If I look at the 2 options, I would say, well, why go to the left? The right doesn't even have the 1, so that should be easier. Let's just take a free body diagram then of this bubble, right? So if we take a look at that bubble, we see something like this, right? With a reaction here that we don't know what it is, called RE horizontal, and a vertical reaction here of 1 divided by 1.6 H. Now, we've cut through the hinge here, therefore there is no moment, but there could be, of course, a shear, which we can call it V1. And there could be, of course, an axial force, which we can call N1 at the hinge, right? And there is nothing else because this one is not in our bubble. It's on the left side of the hinge. Had I taken the other free body, then I would have had to include the 1. But on this diagram, I do not have the 1 included, and from this free body I can say summing moments about C equal to 0. Taken clockwise to be positive, we have plus R E H times H minus 1 over 1.6 H times the distance from here to here is 0.8 H is equal to 0. These two H's cancel, that's a 1/2, and so we get that REH is positive 0.5, and that's 0.5 divided by H, right? 0.5 divided by H. Now that I have REH, which is equal to 0.5 divided by H, I can eliminate this dotted thing here, and just instead of having a symbol there, just point that this is equal to 0.5 divided by H. Then, from sum of the forces in the x direction on the initial free body diagram, we have that this reaction is 0.5 divided by H, and we have completed the statics on that were needed to calculate the reactions, right? I'm going to erase this here also, which is taking space. So those are the reactions on the unit load diagram. Now we realize, what do we need? We need to have the equations that describe the moments everywhere and the equations that describe the axial force everywhere. That requires selecting coordinates and making decisions on what we want to call positive. So if I wanted to expedite things, I could say, notice that this is equal to that and things like that. I'm not going to do that. I'm going to take a look at it as if I can't really see anything, and I'm just going to systematically go step by step. So first I start on the left and sweep my way to the right, or maybe just do this part and then the other part. So my first free body diagram, which I will erase after, is that bubble. So from that bubble we have a bar here like this. We have 1 divided by 1.6 H, and we have 0.5 over H, and we just took a cut over through there, right? Therefore, in general, there is a shear there. In general, there is an axial there, which I can choose any directions I want, right? And in general, there is a moment there, which I can take any directions I want. This one I can call, will be called N1. This one is V1, and this one is M1. Now I need to set up coordinates, right? Because those values are going to depend on where I am. So I'm going to say that a coordinate that starts here and goes upwards is called Y. So when we are at Y equal to 0.2H, we are at 20% of the height, right? So given that definition, this distance here is Y. And now we can do statics. Summing moments about point O, which is the place where I just cut through in the bubble, I can say sum of the moments about O equal to 0, taking clockwise as positive. I have M1, that's clockwise, minus 0.5 over h multiplied times y. I don't see anyone else having a moment, therefore that is equal to 0. And we find that m1 is equal to 0.5 over h times y. Now, we no longer have freedom to decide what is positive on bar AB. We've decided that this is positive, okay? So in this bar, this sign convention is what is positive. Now, if we sum forces in the y direction, equal to 0, taking up as positive, we find that N1 minus 1 over 1.6 h is equal to 0, and therefore N1 is equal to 1 over 1.6 h, right? All right, so with those results, and because of our limited space, we erase the bubble, take this off for a minute. We transplant them to this sketch, and we say on this bar M1 is equal to 0.5 y over h, and N1 is equal to 1 over 1.6 h, and y was this way. And then we can go like this and erase this work, because we got what we wanted out of it, right? We know what's going on in bar AB as far as the M and the N go. Actually, it is a simple matter, right, to note that if we take the free body diagram here, the results are going to be identical as what we just got, except for a sign that depends on what we do with the N1 and M1. In any case, I'll just speed my talking a little bit, but let's say that I took that bubble. So from that bubble, we would have this. This is 0.5 divided by h. This is 1 divided by 1.6 divided by h. And over here we have, are we free to choose sign convention here? Yes, because we have never touched that bar before, right? We're looking here, so I can say there is a shear, V1. I can say there is an axial, and even though I took the axial going up on this bar, I can take it going down on this one if I so desire, because I don't like to deal with negatives if I can afford it. So I take this N1 coming down, and what? And then I need a moment, and in this case I'm going to take the moment this way, so I also get a plus. So this is my M1, N1, and V1. In this case, I could call this variable that starts here and goes up a different name than this one. But if you think about it, they are exactly the same, because being at 20% of the height is the same on either side. So a y is a valid name for the variable that starts here and goes up, because it is really the same. Therefore, we can use our statics and say, summing moments about O, we would have minus m1 plus 0.5 h times y, and so we would find that m1 is equal to 0.5 h over h times y, right? So that would be our m1. Likewise, summing forces in the y direction, we would find that n1 is simply equal to 1 divided by 1.6 over h, and we can come here and transplant our results to the structure over that bar. So we can say this bar has a moment m1, which is 0.5 over h times y, and has an axial force n1, which is 1 divided by 1.6 over h. Even though that axial force here happens to be compression and that axial force there happens to be tension. They both appear plus y because on this sketch I decided to call that positive, and on the other sketch I took the opposite direction. Now I'm committed to those two, but that's fine, right? So if you like, this is compression plus, this is tension plus. Okay, so we can erase. And now we have to deal with the horizontal bar. So now to deal with the horizontal bar, I'm going to have to take free body diagrams of the two sides. So I'm going to go with this free body, right? And from that free body, I can see that I have something like this and like this. Over here, there is a reaction of a half over h. And over here, there is a reaction of 1 divided by 1.6 h. Now I can see that over here, am I committed to any sign convention here on the shear axial end moment? No, because we have not looked at bar CD at all. Therefore, I can say that I have a shear in whatever direction I feel like, that I have an axial in whatever direction I feel like, and that I have a moment, and in this case I'm going to take it to be this way in whatever direction I want. Okay? Now I can see that this moment is going to depend on distance from here to here, and so I need a coordinate, right? So I'm going to say that this coordinate needs a name, which is something that starts here and moves this way. So I'm going to call it n. No, not n. I'm going to call it x. Actually, why not? N or x is the same thing. So n. So I have a coordinate n coming that way. So then if n starts there and comes this way, this distance is n. Okay, that's the complete free body. Of course, we know that this height here is h, which I don't show to keep it as uncluttered as possible. Now we can say summing moments about O, to get rid of the n1 and the v1, we have minus m1. I usually use clockwise as positive, so I have minus m1. Then we have minus 1 divided over 1.6h multiplied times n. That's also negative. And we have positive 0.5 over h, right, multiplied times h. And then that must all be 0. And that tells us that m1, the moment, passing it to that side, is equal to 0.5 minus n divided by 1.6 h, right? And so that is our moment. Where do I have? Just looking at my final summary here, just make sure I don't have any signs wrong or anything like that. Okay, so I have that, that's fine. And then, oh, I need my N1, right? So summing forces in the x direction, we find that N1 is equal to 0.5 divided by h, right? So we have the M1 and the N1, at which point I come here, I erase this bubble to unclutter the drawing as much as possible, and I write that over this bar we have M1 equals to 0.5 minus n over 1.6h, and that I have N1 equals 0.5 over h. Okay? So we are done with 3 out of 4. I take my free body diagram that I used and I erase it because we don't need it any further. Of course, we need the sign conventions when we do the next free body, and that would have been nice to keep somewhere, but I don't have space. But we'll remember, and I have in paper. So our last thing is this bubble, right, that cuts through this bar. And so it looks like this. Over here we have 1 divided by 1.6h plus a horizontal, which is 0.5 over h. Do not make the mistake of including the 1, right? Because you are not cutting. Your bubble is anywhere within this point, right? That 1 only shows up if this bubble is all the way to the hinge, and this is a generic bubble. So over here, since we have not dealt with this bar, we can choose any sign conventions we want. So it's going to be my shear V1. This is going to be my axial N1. And I need a moment, which I am going to take to be this direction equal to N1. Again, just like in the other free body, I realized that I need to talk about distances from here to here. And so I will have a coordinate that starts at this point, and we can call x. And in that context, then this distance from here to here is x. This again is our point O. And if we sum moments about O, we will find that M1, which is clockwise, minus, right, minus 1 over 1.6 over h multiplied times x minus 0.5 over h multiplied times h must be 0. Therefore, we find that our moment M1 is equal to both of those things with change sign. That's just 0.5 plus x over 1.6 h. And if we sum forces in the x direction, it's obvious that N1 is equal to 0.5 divided by h. Okay, so I erased my bubble on the sketch. When you're doing this in the exam, you don't have to erase anything, you just have to make sure those free body diagrams are clearly shown. In case you make a mistake, it can be graded to see whether it was that you just multiplied 2 times 2 and put 7, or whether there was an understanding issue going on. So now that we have that in this bar, our M1 is 0.5 plus x divided by 1.6h, and our N1 is 0.5 divided by h, and our x, of course, was starting there going to the right. We can erase. And this is our unit sketch complete, right? We have the moments and the axials in all the bars as a function of coordinates that are clearly defined. One of the things that is a major problem is when a student gives a result, for example, and says that the moment here is equal to this times x, and there is nowhere to find what x is. If you use a variable, you have to make sure that the origin and the direction in which that variable is going is clearly labeled, otherwise it's meaningless. So here I'm using y, so y is this. Here I'm using x, and x starts here and goes to the right. Here I am using n, and n starts here and goes to the left. Here I'm using y, and it's the same y here. It goes up from the bottom. So that satisfies the requirement. Now, in order to unclutter it a little bit, I'm going to take these dimensions off. We already know them by heart, 0.8, 0.8, and h. And this is our p-sketch. We need to do exactly the same thing as we did there to calculate what is the MP, the NP throughout this structure. As in the previous case, we can say, can I get away without calculating the reactions? It doesn't seem like I can. So I think I'm going to have to calculate the reactions. So first I take a look, well actually let's see, maybe I don't need to complicate the situation necessarily so much. It's clear, I'm going to assume that this is obvious. It's clear that if I take a free body diagram of the complete structure, right, I'm going to have a reaction here, and two horizontal reactions also, right? Which I can take in these directions. Now, from some of the moments about this point, we will find that this reaction is P over 2, and from some of the verticals, this reaction is P over 2, and we cannot calculate from the free body diagram of the whole thing what is the reaction at A in the horizontal or what is the reaction at E in the horizontal, right? Those cannot be computed from the free body diagram of the whole thing. We have to, again, come back to the same thing we did previously, which is to take a free body diagram that takes advantage of the fact that we know that point C has no moment. Now comes the issue of where is P, is it to the right or to the left of the hinge? As I said, you can put it on any side you want, but once you decide which side it is, that's the side in which it is. So I'm going to assume that P is on the left side of the hinge. Therefore, my free body diagram that I'm going to draw right now, which is this bubble, does not have the P, because the P is on the left side of the hinge. By how much? By infinitely small. So my free body diagram now looks like this. There is no P, but there is a horizontal reaction here that we don't know what it is. It's called RE horizontal. There is a P over 2 going up. And at this point, there is a shear. Now, can I take that shear in any direction I want? No, I cannot, because that shear must be in the direction that it was assumed previously, which was pointing down. And so that shear is like that. Wait a minute, no, I'm sorry, I take that back, erase. At this point I'm still just calculating reactions, so it doesn't really matter. All I'm trying to do is getting ERH. So there is a shear, there is an axial force, and there is no moment, right? So that is a complete free body diagram of that bubble. So there is a V and an N here. If we now say sum of the moments about O equal to 0, we would find that sum of the moments about O equal to 0, clockwise is positive, gives us REH multiplied times H, right, minus P over 2 multiplied times that distance, which is what? 0.8 H is equal to 0. From here, the H's cancel, and we find that RE horizontal is just 0.4 of P, right? So I can then come to our sketch, erase the bubble for clarity, actually I guess I don't really need these reactions anymore, so it's probably better for clarity to just have the thing as clean as possible. So it's like that. So this one now proves out to be, and it gives you more space. So this one is 0.4 P, and that's P over 2. And then sum of the forces in the x direction equal to 0 clearly tells us that this is 0.4 P. And so we're there, right? we've completed the computations of the reactions on the P-sketch. I erase this space to give us a little room. And now we embark on the computation of the same thing that we did here, but on the P-sketch. So we begin by finding what is going on the bubble that is going to describe what happens on the left side column. We are now not have any freedom regarding sign convention. We have P over 2 here and 0.4 P here, and we have a shear, an axial, and a moment at that location. And our sign convention, let's see, from before, is that this was taken going up. So I must say that this is NP. The moment was taken this way, so that is MP, and the shear doesn't really matter because we didn't use it, right? So we are like that. Now, in other words, these two signs are consistent, not with what's going to give me plus. They've been determined by the signs that I assumed, by the positive directions that I assumed when we did the one on that bar. So now from here we would say sum of the moments about O equal to 0. Clockwise is plus, gives me minus 0.4 P times Y, right? Plus MP, and I think that's about it. So we have that MP is equal to 0.4 PY. And from sum of the forces in the Y direction, we have NP plus P over 2 equal to 0, or NP is equal to minus P over 2. And so we finish what we can do with, or what we need to do with that bar. So I can erase this thing and transcribe the result to this bar as MP equals 0.4 PY, and NP equals minus P over 2, right? We erase here. So that we can continue. And now we take, let's say, this bubble, right? And that bubble, it's essentially exactly the same thing. So we have P over 2 here, 0.4 P here. This distance is Y. And the sign convention on that side was that the moment was this way. So this is MP. And it was that the axial force was this way. So that must be MP. There is also a shear, and I don't care because we're not using it. So this NP and this MP are not arbitrarily drawn. They are in the same direction that I used when I looked at this bar when doing the one. So now with this condition and this being 0.0, we sum moments about this point. We have 0.4 P times Y clockwise minus MP equal to 0, from where NP is equal to 0.4 PY. And we say sum of the forces in the Y direction equal to 0, and from there we find that NP is equal to P over 2. Okay? So, not surprisingly, they are the same as in the other bar. We erase the bubble, transcribe the information to the structure, and so NP here is 0.4 PY, and NP is equal to P over 2. Okay? So we are done with the vertical bars, and we now move to the horizontal ones. So let's say I take this bubble, right? And so that bubble looks like this, It has a P over 2 here. It has a 0.4 P here. The distance from here to here has already been specified. The name is the coordinate n. At the cut, I need to have axial shears and moments, and they were already determined to have these directions. Therefore, this is NP, this is MP, and I have a shear that I don't care because I'm not using it. So, now I can do statics. This is my point O, and so I can say sum of the moments about point O equal to 0. Clockwise is plus, so I find minus MP minus P over 2 times N plus 0.4 P times what? H is equal to 0. Therefore, MP is equal to P over 2 N minus, no, plus, no, minus, no, sorry, it was minus MP there, so all I have to do is put it on the other side. Therefore, MP is equal to 0.4 PH minus P over 2 N. And then NP, summing horizontals, is equal to 0.4 P. At which point we erase here. Transplant the results. I don't need these reactions here anymore. I'm going to take them out and just put my MP here is equal to 0.4 pH minus P over 2N, and my NP is 0.4 P. Okay, I will erase, and I am going to stop the video and create a new segment because it's probably already too long and might have an issue.